Hey guys, so we're going to continue learning about acid and base chemistry by doing an introduction to buffer solutions today. Now, you might have heard from other students who've taken this course that buffer solutions were the worst part. They were so confusing, no one could understand them, it's a lot of math. Don't believe what you've heard. If you could do the math in the previous section looking at reaction kinetics, reaction rates, and ice tables, then you can definitely do the math involved with buffer solutions. If you found the math in the previous section really tricky and kind of difficult, don't worry. There are shortcuts for buffer solutions. All you have to do is apply an equation. It's very easy to plug numbers in. And if that still seems kind of daunting to you, remember, we're working with the pH scale here. You can all count up to 14, and that's all you have to worry about for the pH scale. It only goes up to 14. So hold on, we're going to start talking about buffers. Now, what exactly are buffers? What do they do? They basically exist as solutions that resist some sort of change in pH. So whether you're adding some sort of strong acid or weak acid to it, or some sort of strong base or weak base to your buffer solution, the pH is going to stay fairly stable depending on how much of the acid and base you're adding. Obviously, if you're adding 20 liters of hydrochloric acid to 10 milliliters of a buffer, you're going to overpower the buffer. That's not really the capacity they're designed for. They're more designed for a larger volume of a buffer with small additions of an acid or a base. Now, how do they work? How do you get this kind of resistance of the change in pH? Well, buffers are an application of the common ion effect. There's some sort of weak acid or base and a salt with a common species in solution together. So you're employing that conjugate acid-base pair that we talked about at the start of the acid and base section. Now, in solution, there's no real reaction between this conjugate acid and base. The reaction happens when you're adding some other solution to it. So, like I said before, strong or weak acid or strong or weak base. Then, depending on what you're adding into solution, whatever exists in the buffer will be used up to resist that change in pH. So, for example, if you have acetic acid in solution, CH3COOH, and sodium acetate as your salt to make up the buffer, NaCH3COO, and you're adding sodium hydroxide to the solution, then the acetic acid, CH3COOH, is going to react with sodium hydroxide, and it's going to create sodium acetate. So you've got this balancing act going back and forth with these two different species in solution, depending on what you're adding to it. Now, obviously, if you added some sort of acid like HCl, you wouldn't be reacting with your acetic acid in that case, you'd be reacting with the sodium acetate, and you would end up forming acetic acid in solution. Easier to understand buffers when you're actually working with them, when you're talking about making the solutions or doing titrations with them, adding things and actually seeing how they function. So that's what we're going to look at next. However, if you don't really remember the common ion effect, any of the ice tables, then I suggest you look over your notes from the previous section just to refresh your memory and reacquaint yourself, because we need to take those concepts learned in the previous unit and apply them again here for acid and base chemistry. Now, how do we make a buffer? What are you going to do when you get to the lab? What are you going to do if you're running a Virtue Lab simulation? How do you actually physically make this buffer? Well, there's three ways. First way is if you take a weak acid and you add a small amount of a strong base to it. Then a little bit of that weak acid is going to get converted, because of that strong base being added, into the conjugate base in solution. So then you've got that weak acid conjugate base pairing. The next method is if you take some sort of weak base and you add a small amount of strong acid to it. Again, you're going to convert that weak base, because of the addition of strong acid, to the conjugate acid in solution. So you're going to have a balancing with your weak base and its conjugate acid. And then the last method that's a bit more difficult to understand is if you're adding a weak acid or base and a common salt. So like in the previous example with acetic acid, we added sodium acetate to it. They both had that acetate ion. That was the common ion for the salt. So working through an example here, how many grams would we have to add of some sort of conjugate salt to a mixture of an acid to make a buffer with a very specific pH? Now, this could be like kind of daunting for you guys, because I'm telling you exactly what pH you have to make. But in reality, knowing the pH makes creating the buffer so much easier. So if you want to try and write out this equation, if you want to try and think about what needs to go into solution, play with ice tables, play with some calculations, go ahead and do that now. Pause the video, pull out some scrap paper and start playing with it. I'm going to go on to the next slide and go through my way of solving this kind of problem, which I think is very straightforward and should be easy for you to understand. All right, so my apologies for just taking a picture of my handwriting here. However, I find it extremely difficult to do all these equations inside PowerPoint, and I thought this was the easiest way to present the information in a way that you could understand. So first things first, we want our buffer to have a pH of 10. Well, we know there's this relationship between the concentration of hydronium, H3O+, and pH. So if we know what our pH is, we can figure out what the concentration of hydronium has to be. That's 1 times 10 to the negative 10 moles per liter. We also know we have this kind of relationship happening in water. We're given what the Ka is for that. So we can write out the acid dissociation constant for this expression. So it's always products over reactants. Liquids and other pure substances like solids do not factor in. So our Ka is H3O+ hydronium, multiplied by the concentration of CO3 negative, divided by the concentration of HCO3 negative. Straightforward, you guys know how to do this. You've done this math before in the previous section. We were looking at reaction rates. No big deal. How much of our conjugate salt needs to be added to solution? We're really concerned about what the concentration of that species needs to be. So you can pull it out and rearrange the equation, and then fill in the information that you have. So you're given what the Ka is, you can plug that in. You know what the initial concentration of the HCO3 negative is. That's given again in the question. And you know what your concentration of hydronium has to be. That's basically given to you in the question because they're telling you what the pH is. So you can go through and solve for the concentration that you're supposed to have of this salt species, this conjugate base species. Now, you've got the concentration, but they're asking for grams. So the next step you're going to have to do is figure out how many moles you need, knowing that your concentration is in moles per liter. So multiply by the liters of solution that you need to have, 1.5 liters, to figure out how many moles you need of that species. And then it's really straightforward. We're calling back to last semester to figure out how many grams you have. Just multiply by the molar mass of your salt. So in this case, if you add 15 grams of that conjugate salt to solution, you'll have a buffer with pH 10. Now, the next thing to think about with buffers is how useful they are, how great they are. If you remember when I was talking about the introduction of buffers, I said that they're really designed to have a larger quantity of buffer and a smaller quantity of acid or base being added to them. And that's because buffers are really considered useful if they resist pH changes of plus or minus 1 unit for every 1 liters of buffer solution. So remember to make a note that's a buffer solution, not the solution being added to the buffer. So if you had just a container full of water and you added 10 mils of HCl to it, you would have a drastic pH change. It would be more than 1 unit of pH change. If you had a buffer solution, you added that 10 mils of HCl, then hopefully it wouldn't go more than 1 unit from what the buffer pH was, meaning that you would have an effective buffer. Now, buffers can be kind of made more useful, more effective, if they have more concentrated components within them. And if you think about it, it just means that you've got a greater amount of those conjugate acid-base pair species in solution to react with whatever's being added to the buffer, so they won't be used up as quickly. The other way you can kind of increase the usefulness of your buffer is if you tailor it to its known purpose. So if you know that you're going to be adding just acid to your buffer, you want to make sure you've got lots of basic species available to it. And this will tie in with one of the videos that you're going to watch later on. Now, going back to our previous example, do we actually make a good buffer? Would it resist those pH changes? If you look at the moles of our acid here, you can calculate it out knowing what our volume was. And you find that we had 0.3 moles of acid in solution. And then this came out in our calculations 0.14 moles of our conjugate base salt is being added in. So if you divide one by the other, you get about 2. So okay, yes, since pH is a logarithmic scale, you just need this number to be somewhere between 0.1 and 10. 2 falls within that range, so yes, we did create an effective buffer. It will resist pH changes. So it's a good little check for you guys to do when you're making your buffers, or if you're thinking about buffer calculations, just dividing your acid by your base and see if it falls into that range of 0.1 to 10. Now, how else can we make buffers? What if we don't have conjugate salt? If you remember, I said there's other ways of doing it. You can add strong acid or strong base to a weak base or weak acid. So that's kind of a taste of what we're going to get into tomorrow, looking at titration curves and how we make buffers. But you can see here, if we had NH3, so ammonia, and we were adding HCl to it, we start off with a fairly high pH because, again, we're starting off with some sort of base, it's ammonia. And then as you're adding acid to it, the pH is falling down until you end up getting the pKa of NH4+. So you have that equivalency between the two different species in solution. So that's the midway point of a buffer. So you know that from wherever you started to that point, it's about half of making your buffer, and you can add about the same amount of solution before you really drop off and become acidic. So we're going to go into that next time when we talk about the Henderson-Hasselbalch equation and titrations with buffers, but just a little preview of what to expect. Now, I know I've posted some other videos and some other comments and activities online, so be sure to check those out and complete whatever you need for our next class.